All right, everybody. So we, in the last video, started to reformulate our thinking around the derivative, where we think of the derivative of a function as a function itself, right? It's a function that spits out the values of slopes of tangent lines, right? So if you're given a function f, you compute this f prime of x, and you input the value of x where you want to know the slope of the tangent line, and it spits that value out for you, as long as that exists. And I've written down a little shorthand for our definition, right? So wherever this limit exists, we have what we call a differentiable function. So let's do a couple of examples. So the first one here, I've got f of x is 3x minus x. So if I wanted to compute f prime of x, I'm going to take the limit. Where's my... Take the limit as h approaches 0 of f of x plus h minus f of x all over h. This will be the limit as h goes to 0 of 3x plus h minus 7 minus 3x minus 7 all over h. We get the limit as h goes to 0. I'll distribute that 3, we get 3x plus 3h minus 7. Let's distribute that negative, minus 3x plus 7 all over h. Now a whole bunch of things cancel, 3x and the negative 3x, 7, negative 7 and 7, all of that is 0. We're left with 3h over h. Of course, we can cancel these factors, and so we're left with the limit as h approaches 0 of 3, and we end up with f prime of x is equal to 3. Okay, now this is still a function, right? This is a very simple function. For every input, the output is 3. It doesn't change, right? So let's examine why that is. Here is our, here's a set of axes. So 3x minus 7 is going to look something like this, right? So it's going through 0, negative 7. I should probably draw it steeper, but it's a little easier to see this way, right? So just say that y-axis scale is, there's more there. That's longer than the actual one is. So what does this derivative function do? So the derivative function, let's graph that one as well, is going to be a horizontal line at the value 3, right? So it's going through the axis here at 0, 3. What is this telling us? Well, what is the tangent line, right? The tangent line, we said, was the line that looks most like our function at a point, right? When we have a curving function and we want the tangent here, we're trying to find a line that if we were to zoom in, right, in here, they look very similar to each other. Well, what's the line that looks most like this line is itself. At any point, if I want to come up with a line that looks like this line, it's going to be that line. Meaning the slope of the tangent line is going to have the same slope as this line does, which is 3. So it's only spitting out 3 because the slope is always 3 for the tangent line of something that's already a line, right? So this is good that this worked out this way. It matches with what our intuition is. Right. Another way to think about it is that this function, the slope of the tangent line of this function is not changing, right? So when we have a linear function, that's really what it means, is that the rate of change is constant. That's a good way to think about what linear functions are. And so the tangent line slope function, which also tells us the value of the rate of change, is also constant. It's only spitting out 3. So the slope of that red line is constant, which means the function, the derivative function, the derivative is constant itself. Okay. So there's a pretty straightforward example. Let's do another one. Let's look at g of x is equal to 1 over x. So then g prime of x will be the limit as h goes to 0, g of x plus h minus g of x over h. Limit as h goes to 0, so we'll have 1 over x plus h minus 1 over x all over h. We can get common denominator by multiplying the first term. So I'm getting a common denominator in the numerator by multiplying each term by 1. So I'm going to get x from the first term, and then I'll get minus x plus h all over x times x plus h. I've still got this h in the denominator. Let's just write that as a 1 over h. So now, when I distribute this negative, I got a negative x. So I got x minus x is 0, and I am left with a negative h. And in the denominator, I'm going to just leave this alone for now. I've got a common factor of h in the numerator and the denominator. So I can cancel that factor or just think of it as a 1. And I'm left with negative 1 x for x plus h. Okay. Now, this limit cares about h. X is some number. Okay. X is some number. And so we can think of this like a rational function where h is the variable. And we know that rational functions, to take the limit, we simply plug in the value. And as long as they're defined, everything works out. So let's try that here. If we plug in h, the limit as h goes 0, put in h equals 0, we get negative 1 over x times x, or negative 1 over x squared. Okay. This works as long as x is not equal to 0, right? And that's fine because we don't care about x equal to 0 because our function's not defined there anyways. So we were really looking over the domain of g, and this is defined over the domain of g. So here's our derivative for g of x is negative 1 over x squared, right? So what is this telling us? Well, if I compute g prime of 1, I get negative 1 over 1 squared, or negative 1. It's telling me that if I look at the graph of 1 over x, something like that, right? It goes through the point 1, 1. If I were to look for the tangent line at x equals 1, oops, let's move that back where it belongs. This line would have a slope of negative 1, which certainly at least seems reasonable from the drawing, right? And if we wanted to compute the equation of the tangent line, I can use the point slope form. The point it goes through is 1, 1, so I get y minus 1 is negative 1 x minus 1, right? If you feel like isolating the y, that's fine. Negative x, we'll get plus 1 from here, plus 1 from there, plus 2, or 2 minus x, which looks like the line that I drew. Right. So this is a we could now find the next, if we wanted to find another tangent line at g prime of 8, it's negative 1 over 8 squared, or negative 1 over 64, right? And so instead of having to go through this whole limiting process again, as we did when we only had the limit at a point, I can compute multiple limits quickly. It's also important that we remember that the derivative is a function on its own. So let's go to a graph. Oops, all right, there is our the work we just did. Here's a graph of g of x, right? 1 over x. And here's the green graph that just came up is negative 1 over x squared. There's the derivative, right? And this is a perfectly good function. We'll see later, I could then take a derivative of this function. We can do a derivative of a derivative, and we'll talk more about that later. But I also want to point out how these two graphs are related. Let's look closely at the blue line. Let's think of a value sort of near -5, right? Imagine that tangent line there. Right? If you imagine the tangent line, it should seem like it's probably going to have a slightly negative slope. It's going to be very flat, not quite perfectly flat, but slightly floating downward. So negative slope near 0, right? And in fact, there's a picture of that graph at the tangent line at -5, right? So if you think about the slope at x equals -5, putting it into -1 over x squared, we'd have -1 over 25, right? So -1/25, which is a very small value, near 0, but negative, right? Well, looking at the graph of the derivative, notice the value of that graph at -5 is -1 over 25, -0.04. Well, what's going to happen to this tangent line as we move from x equals -5 towards 0, right? We're following that blue line down. That blue line gets steeper and steeper, pointing negative. So we should be getting larger and larger negative slopes. What's happening to the green graph? It's shooting down towards -infinity itself, right? It's getting larger and larger negative numbers, right? And you can see that red line looks almost perfectly vertical. It's not, but it's getting very close to that because it's extremely negative. Right there is when I try to put in 0, it disappears. So here's as small as this program will go right now is at x equals -1/10. So its slope would be -100, right? 1 over 1/10 squared, or 1 over 1/100th is going to be 100, and then we've got the negative out front. So here's the thing with a slope of -100. If you move this line, if you move 1 unit to the right, you move 100 units down, right? If we had a more sophisticated program, or maybe if we zoomed in, we could take -1 over, look at x equals -1 over 1,000, and then you'd have 1,000 squared, but negative as your slope, right? Let's pass over 0. Now notice we have slopes. Now we have the slope to the tangent line to the right half of our function graph, the blue part on the right side. It's still a negative slope, right? That curve up is still angling towards the y-axis, and so that the tangent line coming down is still going to have a negative slope. And our green graph that represents the slopes of the tangent line is very negative right there, representing that slope. But as we move away from 0, as we let that x get larger and larger, notice what happens to the blue graphs. It starts to flatten out. The slopes of those tangent lines start to approach 0, right? They're getting flatter and flatter and flatter and flatter. And we see the green graph doing the same thing. It's getting, or not doing the same thing, representing that by getting values that are closer and closer to 0. They're negative. It's got that -1 over x squared. X squared is always going to be positive, so they're always going to be negative. And you can see these tangent lines that I'm graphing look to be negative. This one, for instance, is -1 over 25 again, right? That's the slope of that. Okay, I know these pictures can get quite complicated. We're trying to connect a lot of different ideas together. And we'll do more of it, and you'll want to do a lot of it on your own, because understanding these pictures and how the derivative relates to the function is pretty crucial to us understanding what these derivatives are. Okay, one more thing before we finish this video. Let's just add a little notation, right? So there's a few notations that we'll work with. So if we have a function y is equal to f of x, we've already seen that we can write the derivative as We say this as f prime of x. Sometimes you'll see this dy over dx. Okay, we'll talk more about this one in a second. Or you might see df over dx. These are all representations of the same thing. We also might write y prime or d dx of f of x. This one I think of a little bit like this is an action. D dx says take the derivative of whatever follows. So this is sort of like d dx is saying take the derivative of f. So when we take the derivative of f, we get f prime, the derivative of f, right? So all of these notations are pretty commonly used. We can also relate some of these to when we talk about the derivative at a point. So here I'm not thinking of a as a variable, I'm thinking of a as a constant, some particular number. We can also represent this as dy dx, and then we draw this vertical line and we write the number where we're evaluating it, or sometimes to be even clearer, people might write x equals a, right? We can do the same thing with df dx and x equals a, right? So these are also ways in which we can write down derivative of a point. We don't do these ones on the right as often, but they do come up. So it's good to know, and you might see them out there. This notation is known as, I think people call it Leibniz. I'm never sure if I'm pronouncing that correctly, Leibniz notation. So Newton and this guy Leibniz were credited as being inventors of calculus. In the day, Newton got more credit, but they used slightly different notations to talk about it, and we still use both of their notations today. And it's worthwhile. I think it gives us a little bit of intuition, seeing where this Leibniz notation came from. So let's do a quick explanation of that. So I'll draw a function in, call this f of x. Let's pick a point a, f of a. And then we'll have another point a plus h, f of a plus h up there. And let me just draw two horizontal and a vertical line. This horizontal line, we're going to call this delta x, right? It's just the difference between, in the x coordinates, these 2 points. And we'll call this delta y, the difference between these 2 y coordinates, right? If I drew the secant line, pretend that actually hit where it was, oh, I can make it a little better. Let's try one more time. All right, so there's our secant line. The slope of this secant line can be simply written as delta y over delta x. You've probably seen something like this before. Well, if we take the limit of this slope as delta x goes to 0, what does that mean we're doing? We're shrinking this horizontal distance between a and a plus h. We're letting h go to 0. It's the same idea. We're just using a different notation. So shrink that difference between them. And we can call that's what we call dy dx, right? So these delta y's and delta x, we then, as we shrink them, go to switch over to dy dx. This is a pretty common notation that the delta is kind of like, it's usually still small, but like a handleable small size, whereas dy dx, we're talking about infinitely small, right? It's kind of a trickier thing to get our head around. But this is another way that we can formulate the idea of the derivative and where this notation comes from. It seems like a ton of notation. We're going to be using it a lot, and it tends, if you're practicing and working with it and watching other people work with it, it tends to sink in pretty quickly. Okay, that is it for this one. Thanks, everybody. I will see you next time.